Hey everyone. So, welcome to this video in which we're going to do a quick review of the tanh neuron. Why are we doing this? Well, the idea of this course is to try and give you an understanding of how classification works with neural networks. And we're going to do that by building an email classifier. Now, we're going to start with our neural network. And in this video, we're going to focus on the neuron that we're going to use to build this network, which is the tanh neuron. Now, the network architecture for this course is going to be a simple multi-layer perceptron, right? And so understanding the tanh neuron, which is going to be the core unit of this network, is key. So we'll kind of understand the theory and then quickly implement a version of the neuron. So what is a neuron, right, when it comes to neural network? Well, typically for this multi-layer perceptron, what a neuron does is take in the inputs, right, which comes into the neuron, which is typically all the outputs from the previous layer, or if it's the first layer, the input of the network. And then the first piece of the neuron is a linear layer. We'll look at that in a bit. What the linear layer does is gives you an output, which we're going to call Z. And that then is passed to an activation function. We're going to call that A of Z. And that is our tanh function for this particular video. And what the activation function does is add nonlinearity to this neuron. So otherwise, what you'd end up with is just a set of linear functions, which would be very difficult to model complex problems, right? Especially with most problems having nonlinear behavior. So classification problems would not work very well. So the activation function gives us the nonlinearity, and the output of that activation function gives us the output of the neuron, which we're going to call A. And so looking at the linear part, what happens? Well, suppose you have n inputs coming into that neuron, right? So x1, x2, all the way to xn. What the linear part of the neuron has is parameters. So we're going to call them W, and so it's W1, W2, all the way to Wn. So as you can see, the number of inputs, right, is equal to the number of weights, or putting it the other way, the number of weights you have will be equal to the number of inputs. That way, each input is multiplied by a corresponding weight, right? So that's one part of this Z, which is the output of the linear. And you can think of this weight as a slope, right? That's weighting that input. So if you just had one input, you'd have one weight, W1. And if you have an XZ plot, or in this case, an X1Z plot, you'd see that W1 as the slope, of the line. And then you have a term B, which is added to this product of the weights, right, with the inputs. So you're taking the product of the weight and the input and summing them all up, and then you're adding a bias. And what this bias B does is add that offset, right, to that plot. So it captures any offset from the origin, right? So this is effectively, as you can see, if you have these W1, Wn's, and B set, by training on data, you can see it resembles a linear regression, right? Or it is a linear regression. And so the linear part is effectively that. So we can call it sigma Wixi over I plus B. And these parameters, so Wi, all the W's, and B for that neuron are the parameters that are trained. Now you'll have a neural network where you have multiple neurons in a layer and multiple layers. All of these parameters are trained, and depending on the data are set, right? Okay. And we'll cover training in a future video. Now, if you're training a neuron, what you also need to be able to do is understand the sensitivity of the neuron with respect to the loss function that you're training with. Now, in this case, we're just going to focus on the sensitivity of the neuron with respect to the output, right, of that neuron. So we're going to use chain rule to understand that. But first, let's just compute the sensitivity with respect to Z, right? So we want a sensitivity of the weights with respect to Z. Well, let's take a simple example where you have two inputs, two weights, and a bias. The derivative of Z with respect to W1 is the derivative of this expression with respect to W1, where you just got two inputs, so two weights, right? You can expand this. So you take the derivative of each term with respect to W1, which is just some rule, right, of differentiation. You can see that these two terms go away because there's no dependence on W1, right? What you're left with is this term. X1 is independent of W1, so X1 can be brought out of the derivative, and the derivative of W1 with respect to W1 is 1, so you're left with X1. So you see the derivative of Z with respect to W1 is X1. And this applies for each of the other weights. And so the derivative of z with respect to any w, we're going to call that wi, is xi. So with respect to w2 is x2, with respect to w3 is x3, and so on. What's the other parameter? The weight. So the bias. So you need the derivative with respect to the bias. Again, same differentiation, but now the only term that shows up is this. The other two are independent of b, and the derivative of b with respect to b is 1. So the derivative with respect to the bias of z is 1. And then we want the derivative with respect to the inputs, because if this is a neuron in one of the hidden layers, right, meaning it's not the first layer, then you need to pass back the sensitivities. And so you need the derivative with respect to the inputs. Now again, same process. And now there's no dependence here on these two terms. The dependence is only here, and it's only on the x1. So w1 can be brought out because it's independent of the data, right? Or the input rather. And what you're left with is the derivative of x1 with respect to x1, and the w1 is outside, that is 1, and so you're left with w1. So as you can see, just like with the weights, that can be applied to any x coming into this neuron. The derivative of z with respect to any xi is w. So we've got the derivative of the linear part with respect to the inputs, the weight and the bias. Now what do we have? We have the second part, right? Which is the nonlinear part, which is the activation function. And we're using a tan H activation. So we're going to take this z, and the activation function is basically going to be the tan H of z, right? The hyperbolic tangent, which is a trigonometric function of z. That's it. It's very simple. So what is the tan H function? Well, it's this function, right? You give it an input, and it's going to give you this output. What do we see here? Well, for very negative values, it just almost constrains the output to be very close to -1, right? This is, you'll see a few, a few orders of a few decimal values maybe away from -1, but it's basically -1. As it gets close to 0, so around -2.5, it starts increasing. At 0, you see it's 0, and then increases, and then as it hits around 2.5, it hits 1. So you can see, first of all, this is nonlinear, but what it also does is takes the input and squishes it to be between -1 and 1. So that's what the activation function, the tan H activation function does. And what we need is also the sensitivity of this, right? And so the derivative of tan H of z, A is tan H of z, is the derivative of A with respect to z is the derivative of tan H of z with respect to z. And this is a standard trigonometric derivative, which is 1 minus tan H of z square. Why are we writing it with respect to this? Well, we know A is tan H. And so you can write now the derivative of A with respect to Z in terms of A. We can write it as 1 minus A squared. So the derivative of A with respect to Z for the tan H activation function is 1 minus A squared. Good. So we've got the derivatives, and we also of the linear and the activation function. We also know how the forward pass works. Right? So let's do the forward pass. So we're going to give it a set of weights. We're defining this, right? We're not training this neuron here. That will come when we get to a network, right? And we have kind of built and trained a single neuron model in the deep learning from scratch series. So you can go check that out as well. That will give you a lot of detail. So we are setting the weights W1, W2, and B to be 0.3, 0.5, and 0.1. And I'm assigning the inputs 0.2 and 0.1, right, for this forward pass. And it's just this one neuron. Once we understand this, in the next video, we'll assemble it into a layer. So the first step, sigma wixi plus b. So 0.2 times 0.3 plus 0.1 times 0.5, that becomes what? 0.11 plus 0.1 is 0.21. The tan H of that is 0.207, right? And do check this out. Make sure that it's correct. Now the output is A. Eventually, what you're going to have is a loss function, and you want a sensitivity with respect to that. So now we've got the forward pass, meaning we've taken the inputs and computed the output of this neuron. Now, when you're training this neuron, what you're going to have to do is a backward pass, where you're going to take the sensitivity of the output you care about and compute the sensitivity of each of these parameters and the input with respect to that output. In this case, we're going to call it L, which is typically indicative of a loss function. So that value will be passed into the neuron from the neuron or the layer ahead, right? And we'll understand this more when we get to a layer. And you can also check out the video on building a full neural network, again, as part of the deep learning from scratch series, of course. So dl by dA is actually passed back to us, I'm just going to set it to 1, right? Because we're just looking at this neuron here. So we're saying the derivative of the function we care about with respect to the output of this neuron, and this whole thing is the neuron, right? These two parts are combined is the neuron. The derivative of that with respect to A is 1. Now what do I do? Well, you take this first part and we're going to focus on this function now. And we're going to say, let's differentiate across this. So the derivative of A with respect to Z, we know it's 1 minus A square. And now you understand why that helps, because we already have A from the forward pass. So it's 1 minus 0.207 square, which is this value. Now that we have that, we actually want to compute the derivative of the loss function L with respect to Z, right? And then push that further back. So what can we do? We can use chain rule, and we can say the derivative of L with respect to Z is a derivative of L with respect to A, which we already have from the layer in front. So that's an input times the derivative of A with respect to Z. I've used the whole derivative here because you could just say A is only dependent on Z here. So you can replace this partial actually with a whole derivative as well. And what you have is 1 times 0.957 is 0.957. And so you've got the derivative of A with respect to Z, right? And no, rather the derivative of L with respect to Z. So we've propagated this back, and that's why it's called back propagation. Now, we don't really care about the derivative with respect to Z. That's just an intermediate value. We care about the derivative with respect to W1, W2B, and then X1 and X2. So what do we do? The next step, let's focus on W1. We know dou Z, dou W1, the derivative of Z with respect to W1 is X1, right? We've just derived that. And in this case, X1 is 0.2, so the value is 0.2. So the derivative of L with respect to W1 is dou L dou Z times dou Z dou W1. We've just computed this in the previous step. So we've got that as 0.957 times 0.2 is this value. And so we've got the derivative with respect to W1 by doing. We can do exactly the same for W2 and B. Right? We already know what the derivative is. We've just looked at that in the linear part. Use the chain rule and you'll get the answer, right? So do try that out, and I'll show you the answer at the end in a couple of slides. Same thing for X1, the derivative of Z with respect to X1 is W1. This is important because if it's a neuron in one of the middle layers, you're going to need this value to propagate back through the network, right? And so the derivative of Z with respect to X1 is W1. We know W1 is 0.3. So the derivative of Z with respect to X1 is 0.3. So the derivative of L with respect to X1 using the chain rule is 0.957 times 0.3, which is 0.287. So we've got the derivative of L with respect to X1 as well, right? And so effectively, if you do this for the neuron, assuming two inputs, you'll have two weights and a bias. These are the derivatives you should compute, right? And we quickly implement this. Neuron as the first piece of the puzzle we're implementing, right? And then over the next few videos, we'll kind of make that a network and then add the activation function and then the loss function and then train to classify it. And so the summary, we have a neuron like this. It's a tanh neuron. It has a linear part, and the forward pass would be the sum of the weights, the product of the weights times the inputs plus the bias. And the activation function is a tanh, so this would go in here. And for the derivatives, and this is how we'll implement it because we now know it. We're not going to do a forward and a backward specifically. Now, again, you can go back to the videos that I just mentioned on building a full neural network or a single neuron model in the deep learning from scratch course. And there I go through this line by line. Here, I'm just going to use this implementation, right? So dou A by dou xi, the derivative of the output of that neuron with respect to the x is 1 minus A square, which is the output, which will be computed in the forward pass times Wi. The derivative of A with respect to the weight is 1 minus A square, which is of the tanh times the corresponding input. And the derivative with respect to the bias is just 1 minus A square because this is actually 1, right? The derivative of Z with respect to B is 1. So that should give us the tanh neuron. Hopefully this has given you a good understanding. If it's a review, you've hopefully reviewed it, you've understood the review. And if you want a little more detail, do check out the Deep Learning from Scratch series as well. But I think this is comprehensive enough, right? Okay, so let's go implement this, in code quickly so that we have a neuron, and then we can then in the future videos go and build on that to get the network. Okay, so let's now code up this neuron. as the first part to this email classifier creation course. And so we're going to start, by just implementing this. Now I've got a basic kind of very simple class here. I'm going to call it class neuron. And the init function takes in the number of inputs to that neuron and the tag. So we're just implementing it as a neuron, and then the layers are going to be an assembly of neurons, right? The vectorization at the layer level is not going to be covered in this course. At the end of this, you'll understand classification really well, and then as a short course at the end of that, we'll kind of cover how to vectorize your network for production, right? Okay, so it takes in a tag, and then it takes in the number of inputs, right, which is important. Now what are we going to do? Well, let's just quickly initialize the different values we're going to need for this. So we're going to have the weights of the neuron and the bias, and I'm initializing it to a set of random numbers. The weights is as many weights as there are inputs. The bias is 1, right? 1 value. And then during the forward pass, we're going to be computing x, z, and a, as we've seen in the theory part. And then in the backward, we want a sensitivity of the loss function with respect to the weights, the bias, and with respect to the inputs. Okay. Now we need a way to set the weights and the bias, to a specific value. So you're running an optimization, you've got the values, you need to update it, right? You can't always have them to be random. So we've got this simple update weights function, which takes in w for the neuron. And what it does, well, the last value, which is w minus 1, is the bias. All the other values, so 1 to the second last value, is the weight. So depending on the number of inputs, you can take all those values and you can store them. We could add a check there to check that the size of that is correct. We'll do that when we get to the layers level, right? For now, I'm just keeping this very simple. Okay, so now we need the forward pass. And so what's the forward pass? Well, takes in the inputs x. First step is to compute w1, x1. So you could write this manually. You could do a loop over the index here and do wi xi, right? But we're using numpy, so even though we're not vectorizing at a layer level, at a neuron level we're saying z is numpy dot self.w times x. So depending on the w stored, it's going to do w0x0 plus w1x1 all the way till the number of inputs you have. So that's sigma wixi, and then add the bias to that. And then you have the activation function, which in our case is the tanh function. So you're going to say a is numpy.tanh and you're going to store a, x, and z. And that's it, right? That's our forward pass, very simple. And then we have a backward pass. Now again, a fairly clean implementation. Now, if you've kind of seen the single neuron model or the full neural network we've implemented in the deep learning from scratch course or series, we've done this slightly differently there, right? The idea there was to walk you step by step through how this works. In this case, I'm just doing it in a slightly better, more efficient way. And so we've seen, as you can see on the right, the formula. Theoretically, we know what the derivative of loss with respect to the weight, dl dwi, is xi. And so when you say self.x, it's just the array of all the inputs, and you multiply that by this, which is the derivative of the activation function. And that's the derivative with respect to w, right? xi. So the corresponding wi becomes the corresponding xi times the a. And then, so you can write this as wi times 1 minus a square, right? And for this one, you can write it as, so rather this is xi times 1 minus a square. And for this is wi times 1 minus a square, right? And for the bias, well, it's just 1 times 1 minus a square, where 1 minus a square is the derivative of the activation function, as you can see. So it's just 3 lines of code, very simple. Now what we're going to do is we're going to return these 2 values. And so what we're going to say is we're going to say combining the derivative of x, rather of w and b, we're going to call it dld parameters, which is the parameters of the neuron, and we're just going to combine these 2 arrays. This is actually a scalar value, so we're going to combine dldw with dldb and return that array, and then we're also going to return dldx, right? So we can pass it to the previous layer. when we backpropagate. So we've got the backward pass as well. Let's just see if this works. Okay, this seems to not have a problem. And so what do we do? Well, let's set up the neuron first. We're going to say, call it the tag N1, 2 inputs, and we're going to use the values we used in the theory part. It sets up correctly. Let's now give it a set of inputs, so 0.2 and 0.1, and run the forward pass. You get the answer, 0.2069. We've seen, in the theory, and I'm just putting a quick schematic of that on the right. You see that it was the correct value. And now the backward pass, so we're going to set the derivative that's coming in from the layer in front, or the neuron in front, which is the derivative with respect to the loss function of the output of this neuron A to be 1. We run the backward. Right now we're going to destructure the backward, so it's returning dl dx and dl d parameters. So let's just write it like that, and I'm going to say dl dx and dl d parameters. And now let's print dl, just because these are dl dx, and I'm going to say dl dx, and then print dl d params. Right. The first two will be with respect to the weights, and the last one will be with respect to the bias. So let's run this and then print it. And yes, we've kind of computed this on the theory part. It's pretty much what we're getting. So we're seeing that our neuron implementation is correct, and it's very simple, right? Setting up the neuron is very, very simple. And so that's that, right? Okay. Okay, so we've just implemented the 10H neuron. So the next step here now is to take the neuron and assemble it into a layer, right? And that's what we're going to cover in the next video. So see you in the next one.